All right, so ready to dive into some A-level physics.
Always.
Awesome. Today we're going to be tackling detailed notes section 02, particles and radiation.
Ooh, sounds dense.
It does, right.
Yeah.
But I promise we're going to break it down, make it clear, engaging, and maybe even a little fun.
Okay, I like fun.
Yeah. And who knows, you might even have some like aha moments along the way. What's really fascinating about this section is that it delves into like the very essence of matter itself.
Right to the basics.
Yeah, like the building blocks of, everything around us. Protons, neutrons, electrons.
Right, the dream team.
Yeah, how they interact to create the world we see and experience. So let's start with the basics. We all know atoms are made up of these particles, but what makes them unique?
Yeah, that's the question, isn't it?
Like what distinguishes a proton from a neutron?
Okay, so one key difference is something called specific charge. It's essentially the charge-to-mass ratio of a particle.
Okay.
You can think of it like comparing two athletes, one a sprinter and one a weightlifter. They might both be incredibly strong, but their strengths are kind of expressed differently, right?
Yeah.
Because they're different masses.
Right.
And specific charge helps us understand those differences, but in the context of particles. So their charge and their mass relationship.
So a proton, with its positive charge and a relatively small mass, would have a much higher specific charge than a neutron,
Yeah.
which has no charge.
Exactly. And this difference is crucial because it allows us to actually identify particles based on how they behave in electric and magnetic fields.
Okay.
For instance, in a technique called mass spectrometry, scientists use specific charge to separate and identify different isotopes of an element.
Huh, that's cool.
Yeah, it's like sorting atoms by their unique fingerprints. Pretty neat.
That is really cool. It's amazing how this seemingly simple ratio has such significant applications in the real world.
Yeah.
But speaking of isotopes, I remember learning about carbon dating in school.
Oh, yeah.
How does that tie into all of this?
Carbon dating is a fantastic example of how understanding isotopes can help us unlock secrets about the past. Carbon-14, which is a radioactive isotope of carbon, decays over time at a predictable rate.
Okay.
And by measuring the ratio of carbon-14 to carbon-12 in a sample, scientists can determine its age.
Wow.
Whether it's an ancient artifact or a fossilized bone or a piece of paper.
It's like having a built-in clock.
It is.
That tells us how long something's been around.
Totally.
That's so cool. It makes you realize that these tiny particles hold clues to events that happened thousands, even millions of years ago.
Yeah.
But let's get back to the atom itself. We know protons are crammed together in the nucleus, and since they're all positively charged, shouldn't they like repel each other and just fly apart?
That's a great question. And it highlights the incredible power of the strong nuclear force.
Okay.
Despite that intense electromagnetic repulsion between protons, this force, the strong force, manages to bind them together within the nucleus. It's like an incredibly strong glue that only works at extremely short distances.
Okay, so it's this intense force that keeps the nucleus from just exploding.
It does, yeah.
But if it's so strong, why do some nuclei undergo radioactive decay?
Well, that's because the strong force has a very limited range.
Okay.
If the nucleus becomes too large or has an imbalance of protons and neutrons, the strong force might not be able to hold everything together. It's like trying to build a tower out of magnets. Eventually, if you add too many, the structure becomes unstable and collapses.
Right.
And when a nucleus becomes unstable, it tries to regain stability through radioactive decay, tries to balance itself out.
So that's where alpha, beta minus, and beta plus decay come in.
Exactly.
They're all different ways for the nucleus to kind of like rearrange itself
Right.
and become more stable.
Exactly. Each type of decay involves the emission of different particles and results in specific changes to the nucleus. For example, in alpha decay, the nucleus ejects a helium nucleus,
Okay.
which consists of 2 protons and 2 neutrons, effectively reducing its size and charge. Like it's slimming down, getting rid of stuff,
Gotcha.
trying to find that stability.
And in beta decay, it's all about those mind-boggling transformations.
Right.
Like a neutron morphing into a proton, releasing an electron, or even a proton converting into a neutron, releasing a positron.
Yeah. It is mind-boggling to think about.
It is.
And these beta decays, they involve not only those charged particles, but also the release of nearly undetectable particles called neutrinos and antineutrinos.
Oh, wow.
Yeah. And the discovery of these elusive particles was a major breakthrough in physics. It actually helped solve a puzzle that had been baffling scientists for years.
What kind of puzzle?
Well, when scientists first observed beta decay, it seemed like energy wasn't being conserved,
Uh-oh.
which was a huge problem because the principle of conservation of energy states that energy can't be created or destroyed, only transformed from one form to another.
Right.
So this was a big problem. But the discovery of neutrinos and antineutrinos carrying away some of the energy restored the balance and actually solidified this fundamental law of physics.
So these tiny particles not only participate in these like nuclear transformations, but also uphold one of the most fundamental laws of the universe.
Totally, yeah.
Wow. But things are about to get even wilder, right? Because now we're entering the realm of antimatter.
That's right. Hold on to your hats because we're about to explore a world where particles have evil twins, where matter and antimatter collide in spectacular displays of energy, and where the very fabric of reality seems to bend and twist.
Okay, you've definitely got my attention. Bring on the antimatter.
Let's do it. Welcome back. Last time we left off, ready to dive into the world of antimatter. So let's unravel this mind-boggling concept. What exactly is antimatter?
Right, is it just matter with like an attitude problem?
Not quite. Antimatter is like the mirror image of matter.
Okay.
So for every particle of matter, there's a corresponding antiparticle with the same mass but opposite charge. Think of it as like a cosmic balancing act.
Okay.
That particles and antiparticles always in this delicate dance.
So for an electron with its negative charge, there's an anti-electron called a positron with a positive charge.
Exactly. And it's not just electrons and positrons. Every particle, from protons and neutrons to quarks and neutrinos, they all have their antiparticle counterpart.
Wow. It's like the universe has a secret twin for every particle it creates.
It does.
But what happens when those twins meet? Is it as dramatic as it sounds?
Oh, it's far more dramatic than you can imagine.
So,
When a particle and its antiparticle collide, they annihilate each other in a burst of pure energy.
oh, wow.
Yeah, it's like matter and antimatter are engaged in this cosmic tango, and their final embrace releases a tremendous amount of energy in the form of photons.
So it's like matter and energy can switch back and forth, like two sides of the same coin.
Exactly. And this annihilation process, it's not just a theoretical curiosity, it has real-world applications, particularly in medical imaging. Have you ever heard of a PET scan?
Yeah, PET scan, they use it to diagnose all sorts of medical conditions, right?
That's right. PET stands for positron emission tomography,
Okay.
and it relies on the annihilation of positrons with electrons in the body. So by injecting a small amount of a positron-emitting radioisotope into the patient, doctors can track the positrons as they annihilate with electrons, producing gamma rays that can be detected and used to create really detailed 3D images of the body's internal workings.
That's amazing. It makes you appreciate the interconnectedness of physics and medicine.
It does, yeah.
But let's zoom out for a moment and talk about the bigger picture.
Okay.
If these particles are constantly like interacting and annihilating, what keeps the universe from collapsing into like a chaotic mess of energy?
That's where the four fundamental forces of the universe come into play.
Okay.
They act as the cosmic architect, shaping the interactions between particles and governing the behavior of everything, from atoms to galaxies.
Right. So we've got gravity, the force that keeps our feet on the ground, and planets in orbit. And then there's electromagnetism, the force responsible for like everything from magnets and electricity to the behavior of light.
But what about the strong and weak nuclear forces? They seem a bit more mysterious.
They are indeed. The strong nuclear force, as we discussed earlier, is responsible for binding protons and neutrons together within the nucleus,
Right.
overcoming their electromagnetic repulsion. And the weak nuclear force is involved in various radioactive decays,
Okay.
like a beta decay where a neutron transforms into a proton or vice versa.
Right.
These forces might seem esoteric, but they play crucial roles in shaping the universe as we know it.
So these four forces are like the puppet masters of the universe, controlling the movements and interactions of all these tiny particles.
That's a great analogy, but what's even more remarkable is that these forces, despite their vastly different strengths and ranges, are thought to be mediated by exchange particles.
Okay.
It's like these forces have their own messengers carrying messages back and forth between interacting particles.
Exchange particles, what are those? Imagine two people throwing a ball back and forth.
Okay.
The act of throwing and catching creates a repulsive force between them, right?
Right.
Now imagine them throwing a boomerang, which returns to the thrower. This represents an attractive force. In the quantum world, these balls and boomerangs are the exchange particles, and they carry the force between interacting particles.
So for the strong force, which holds the nucleus together, the exchange particle is the gluon,
Exactly.
like the glue that binds those protons and neutrons together.
Right. And for the electromagnetic force, it's the photon, the particle of light. Each force has its own unique exchange particle, and the type of particle determines the nature and strength of the force.
Okay, so we've got these fundamental forces and their exchange particles zipping around, mediating interactions between all these different particles. But how do we even keep track of all these particles? Seems like a real zoo down there in the subatomic world.
It is a bit of a zoo, but thankfully physicists have devised a way to categorize all these particles based on their properties and interactions. One of the most fundamental distinctions is between hadrons and leptons.
Hadrons and leptons. Those sound like creatures from a science fiction novel.
They do. Think of it this way. Hadrons are like composite particles made up of even smaller particles called quarks,
Okay.
whereas leptons are fundamental particles, meaning they can't be broken down any further.
So protons and neutrons, which are made of quarks, are hadrons. But electrons, which are fundamental particles, are leptons.
Exactly. And this distinction is crucial because it determines how these particles interact with the fundamental forces.
Okay.
For example, hadrons, being made up of quarks, experience the strong force, whereas leptons don't.
It's amazing how this simple classification scheme helps bring some order to this seemingly chaotic world of particle physics.
It does.
But let's dig a little deeper into the world of hadrons. I've heard there are different types of hadrons, like baryons and mesons. What's the story there?
That's right. Baryons, like protons and neutrons, are made up of 3 quarks. And mesons are a bit like a quark-antiquark pair dancing together in this fleeting embrace. These different combinations of quarks and antiquarks give rise to a whole spectrum of hadrons, each with its unique properties and characteristics.
It's like a subatomic Lego set with quarks as the building blocks and baryons and mesons as the different structures you can create.
That's a great way to think about it.
But with all these different particles and interactions, how do we make sure everything adds up? Are there any rules that govern this subatomic world?
Absolutely. In the quantum world, just as in the macroscopic world, there are fundamental laws that govern the behavior of particles and ensure that certain quantities are always conserved. These conservation laws are like the cosmic accountants, making sure everything balances out in any interaction.
Okay, so what kind of quantities are we talking about?
Some of the most important conserved quantities in particle physics include charge, baryon number, and lepton number.
Hold on. Baryon number, lepton number, what are those?
So baryon number and lepton number are like labels that help us distinguish between different types of particles and track their transformations and interactions. For example, baryons, like protons and neutrons, have a baryon number of +1, whereas antibaryons have a baryon number of -1. Leptons, like electrons and neutrinos, have a lepton number of +1, while antileptons have a lepton number of -1.
So it's like each particle has its own unique ID card that helps us keep track of it in a crowd.
Exactly. And the beauty of these conservation laws is that they help us understand and predict the outcomes of particle interactions. For example, in any interaction, the total baryon number before and after the interaction must remain the same.
Okay.
Similarly, the total lepton number must also be conserved.
It's fascinating how these seemingly simple rules can provide such profound insights into the workings of the universe. But we've been focusing so much on particles. What about waves? I remember learning about the wave-particle duality of light. Is light a wave or a particle? Or is it something else entirely?
That's a great question, and it leads us into one of the most mind-bending concepts in physics, the idea that light, and indeed all matter, can exhibit both wave-like and particle-like properties.
Wow.
It's like the universe is playing a cosmic game of hide-and-seek, revealing different aspects of its nature depending on how we observe it.
Okay, so light can act like a wave spreading out and interfering, like ripples in a pond.
Yeah.
But it can also act like a particle carrying discrete packets of energy called photons, like tiny bullets of light.
Right.
But how can something be both a wave and a particle at the same time? It seems impossible.
It does seem paradoxical, but that's the beauty of quantum mechanics. It challenges our classical intuitions and forces us to embrace the strangeness of the subatomic world.
Right.
The wave-particle duality isn't about light being one or the other. It's about recognizing that light, and indeed all matter, possesses both wave-like and particle-like properties.
Okay.
And which aspect we observe depends on the experiment we perform. It's like looking at a coin spinning in the air. It exhibits both wave-like properties, the rotation, and particle-like properties, like landing on heads or tails.
Right.
But we only observe one aspect at a time.
Wow, that's mind-blowing. So those tiny electrons, which we usually think of as particles, can also behave like waves.
Exactly. And this wave-like behavior of electrons has profound implications for our understanding of matter. In fact, it's the foundation of many modern technologies, from electron microscopes to transistors and lasers. But let's delve deeper into this fascinating concept and explore the experiments that revealed the wave-like nature of matter.
I'm ready to dive in. Bring on the wave-particle duality.
Let's do it.
Welcome back to our deep dive. It's amazing how much we've already uncovered about the world of particle physics.
Right, from those tiny building blocks of matter to the forces that govern their interactions, and of course that mind-bending wave-particle duality.
Yeah. It's like we've gone on this incredible journey into the heart of matter itself.
And we're not done yet. Today, we're going to delve into a phenomenon known as the photoelectric effect, which was really crucial in shaping our understanding of light and matter. It's a classic experiment that really highlights the particle-like nature of light and provides further evidence for that quantum nature of reality.
Okay, so the photoelectric effect, it's all about shining light on a metal and seeing if electrons get ejected, right?
Right. But it's not as simple as just shining any old light on it. It's not just about, like, the brightness or the intensity. It's about the frequency of the light.
Right.
Only light above a certain frequency, known as the threshold frequency, can actually cause those photoelectrons to be emitted from the surface. And this was a major puzzle for classical physics because they couldn't explain why the intensity of the light didn't matter as much as its frequency. It was as if the electrons were being picky about which light they would respond to.
It's like there's a secret password to unlock those electrons, and only light with the right frequency knows the code.
I like that, the secret password. And the key to cracking this code was the photon model of light.
Okay.
This model proposed that light travels in these discrete packets of energy called photons, and the energy of each photon is directly proportional to its frequency. So think of it as each photon carrying a specific amount of energy, like a tiny delivery truck carrying a package.
All right.
If the package is big enough, meaning the photon has enough energy, it can knock an electron loose from the metal.
So it's not just about the number of photons hitting the metal, but the energy that each photon carries.
Right, exactly.
If the energy is below the threshold, no electrons get ejected, no matter how many photons are bombarding the metal.
Yeah.
But if the energy is above the threshold, even a single photon can knock an electron loose.
Exactly. And this threshold energy, the minimum energy required to liberate an electron from the metal, is called the work function.
Work function, okay?
Yeah, it's like a barrier that the photon has to overcome to free that electron. So if a photon has more energy, that excess energy, well, it goes into the kinetic energy of the ejected electron, making it zip away.
Okay, so that extra energy gives the electron a speed boost.
Yeah, a speed boost. And we can actually measure this kinetic energy by applying a voltage, called the stopping potential, to oppose the motion of those photoelectrons. And the voltage needed to completely stop the most energetic electrons, well, that tells us how much kinetic energy they had. Like, we're applying the brakes to those speeding electrons.
So the photoelectric effect not only demonstrates the particle-like nature of light, but it also allows us to measure the energy of those particles.
Yeah.
It's pretty impressive. But it sounds like there's a lot more to unpack here.
Yeah.
Is there like an equation that describes all this?
There is, yeah. The photoelectric equation, it elegantly encapsulates this relationship between the photon energy, the work function, and the maximum kinetic energy of those photoelectrons. It's a simple equation, but it's super powerful, and it really revolutionized our understanding of light.
It's amazing how a simple experiment like shining light on a metal could lead to such profound insights. But the journey doesn't end there, right? What happens when electrons collide with atoms?
Oh, that's another fascinating area of study. When free electrons, like those in an electrical current, collide with atoms, they can transfer some energy to the electrons within the atom,
Okay.
causing them to jump to higher energy levels. This process is known as excitation. It's like giving those atomic electrons a boost of energy, allowing them to, like, climb the ladder of energy levels within the atom.
So instead of knocking the electrons completely out of the atom, like in the photoelectric effect, these collisions just kind of bump them up to higher energy levels within the atom.
Right, exactly. But just like climbing a ladder can be tiring, electrons prefer to be in their ground state, the lowest energy level. So when an excited electron returns to its ground state, it releases that extra energy, and it does that in the form of a photon.
So it's like a game of energy ping pong, with electrons absorbing energy, jumping to higher levels, and then releasing that energy as light when they return to their ground state.
Perfect analogy. And that energy difference between those levels, well, that determines the energy and therefore the color of that emitted photon.
So that's why we see different colors when we heat up different elements, right? Because each element has its own unique set of energy levels, so the emitted photons have different colors, creating those beautiful emission spectra we see in fireworks and neon signs.
Precisely. And if a free electron has enough energy, it can even knock an electron completely out of the atom, a process called ionization.
Okay.
So like, bye-bye, electron.
So excitation and ionization are all about electrons jumping between energy levels or leaving the atom altogether. But how do we know that these energy levels even exist? Is there any experimental evidence for them?
There is. One of the most compelling pieces of evidence comes from line spectra. So imagine passing white light through a prism. You get a continuous spectrum of colors, like a rainbow. But if you pass light from a fluorescent tube or a heated gas through a prism, you get a line spectrum. It's a series of bright lines at specific wavelengths.
Okay.
It's as if the prism is separating the light into its individual colors, but instead of a smooth rainbow, we see only certain colors.
So each line in the spectrum represents a specific energy transition within an atom.
Exactly.
It's like a fingerprint of the atom's energy levels, showing us the allowed energy jumps that the electrons can make.
Right. And by analyzing these spectra, we can learn a lot about the structure and behavior of atoms, including, the arrangement of their electrons and the energies associated with those arrangements.
It's amazing how these seemingly abstract concepts, like energy levels and photons, have such tangible and observable consequences in the world around us, from the colors we see to the technologies we use.
It all comes back to the beauty and the interconnectedness of the physical world, from the smallest particles to the largest structures in the universe. And it's a reminder that there's still so much more to discover and explore in this realm of physics.
Absolutely. Well, thank you so much for joining me on this incredible journey through the world of particle physics. It's been an absolute pleasure learning from you.
It's been a pleasure being here. And to our listeners, keep exploring, keep questioning, and never stop marveling at the wonders of the universe. You never know what other mysteries and discoveries await us in the realm of the very small.
Well said. Until next time, keep those physics brains buzzing.